Okay, the lecture 7 is the analysis of the coordinates of a really important group, which is U2, univariate in 2 complex dimensions. It's the one that we've been talking about that does polarization for both the light and for electrons, but also handles the quantum mechanics of any two-state Schrödinger system. And we'll be going over that again, but I would first like to just pick out a small part of what we've talked about in lecture 6 and review that very quickly, a couple of pages for each of these at most. And then today we're going to go into how you do the exponential of a Hamiltonian that's made out of the SU2 generators. That's what the Pauli spinors really would be called in a mathematical setting of modern nomenclature. And I want today to derive that as a exercise that Mr. Hamilton did in order to develop his quaternion theory, which then so many years later became the spinor theory of quantum mechanics. So we're going to make an analogy between spinor arithmetic and just plain old complex arithmetic. Review a few things about that. And then the spinor vector, that's the thing we need to define and be very careful about. And we'll be talking about that in this lecture and in the following lecture 8, which is sitting with its table of contents ready on the next screen. And the most important part of it is putting all that together to make a spinor exponential. And this is what I call the crazy thing theorem. And the crazy thing theorem goes back to the complex function analysis that Euler did long before 1843, which is when Hamilton discovered the quaternions. Now it's 20 years later that John Stokes shows how to do an analysis of optical polarization. We've already mentioned the Stokes spin vector in this previous lecture, and that's one of the 3 famous two-state systems that I'm referring to. Now the geometry and algebra of the U2 evolution is more like a rotation. In fact, it is a R3 revolution. This connection between U2 and 3-dimensional space is really spooky. This is I think, one of the most beautiful things in topology, certainly, but in just plain old analysis of space and time. We're going to just take the spatial part, the time will be for later. And in the connection between these two, one of them, namely this one, is essentially twice as big. And there are mysterious factors of 2, or a 1/2, that keep coming up. We've sort of tripped over a couple of them already that are doing beats. So this 2D spinor versus a 3D spin vector space is really important to get in your head in order to understand a lot of things that have to do with group theory. Now I should point out that these 2 groups have a lot of subgroups, particularly finite subgroups, that we'll be studying later. So we're starting from the top in this discussion of group theory, as far as group theory of things that live in 3-dimensional space. And we'll make a connection with the nuclear magnetic resonance Hamiltonian and the 3D spin moment in a magnetic field at the end of this discussion. Then we're going to go and compare the Euler definition of rotations using this little machine that's sitting out in front of the desk today. And we'll discuss how it can understand both spin 1, which is what vector space, R3 really, it should be called, and spin 1/2, which is the U2 space of 2D complex states, spinner defined. And finally, the Stokes vector of John Stokes will be brought back again. So that's really the first of the famous two-state systems that we've already talked a little bit about, with its A, B, and C we call asymmetry, balance, and chirality. That is, I think, the best way to physically understand what's going on. And a lot of the mysteries that are here become less mysterious for that. So let's do the review very basically here of the 2D oscillators. That's just a Newton's equation, mass times acceleration equals spring constant matrix dotted with the state itself. So the acceleration, if you were to divide the mass, somehow invert the mass into the spring constant, that would be an acceleration equation. That's what's being written right here. That's what it looks like for the examples that we've done so far. So there's the inverse mass having been taken away from the left-hand side. Now, we've already said we need the eigenvectors. That's what this is really all about. But the dynamics that goes with the combinations of eigenvectors is where we want to make clear the group analysis is going. And the basic group idea here is that a differential equation such as this one can be solved using group operators. And that was the dream of Sophus Lie, L-I-E, the Lie group. U2 is an example of the Lie group. It's the first non-trivial Lie group. It's called A1 by some people. It is the beginning of Lie group theory. And his dream was that all of those difficulties that you have with differential equations might go away, he thought, if I could be very sophisticated with some group theory. He's partly right. There's plenty of differential equations that completely seem to avoid any advantages of group, but the ones that we have in the physics of quantum mechanics and oscillators definitely can use this, and that's what we're going to be talking about today. So, and finding eigenvectors, of course, is the thing. Now, here are the three famous two-state systems, states that are describable in our little geometrical approaches by two complex numbers, but each of those two numbers, these amplitudes, is represented by a clock. At any time, the readings on those clocks will give the polar form of the complex numbers that we call wave amplitudes, or spinor wave functions, if we're talking about electron spin 1/2. So this is the, I would guess, number 2 of the three famous U2 applications. The number 1 is right here in the center, and that's John Stokes in 1862. This is 1954. That's nuclear and electron spin resonance, and resonance of spins in general becomes a subject of great interest. And finally, Feynman, Vernon, and Hellworth show up in 1957 with a description of how every two-state system, including the really famous one involving ammonia inversion, ammonia doublet spectra that led to the ammonia maser, and we'll be talking more about that much later, but we'll be using the stuff that we're developing for these two. And as I always say, this is the one that makes the most sense at first. Now, this is quite a page, isn't it? Mm-hmm. This is what we spent about 15 pages discussing in Lecture 6. And the idea was to connect a complex two-dimensional Hamiltonian first-order differential equation with a real spring matrix double order, second order differential equation of basically Newton-Hooke dynamics. And this was a fancy sort of classical Hamiltonian that gave the same equations of motion through Hamilton's equation. Same Hamilton as the spinor business that we're going to be doing, quaternion business we're going to be doing. And here was the actual quantum mechanical equations written out in their real form. There's 4 real equations sitting there that have come out of this. And then I take that and make a second order equation out of it that matches the Newton-Hooke equation. And then I point out in lecture 6 that you could have done this very easily by simply taking the time evolution operator in its abstract form, which is a matrix consisting of A, B, C, and D parameters, and just square that. If you square that, you get a matrix that's like that is for C equal to 0, matchable, matches onto this Newton-Hooke equation. So it's kind of like saying the square root of the stuff that's going on in our real equations becomes the Schrödinger spin analysis that we're going to be doing today. Okay, now I pointed out that Hamiltonian, that little 2x2 Hermitian operator that generates through an exponential unitary transformations of spin states. This Hamiltonian is a linear combination of some very famous operators. Reorganizing this thing just a little bit, I don't change this and I don't change that, but I do change these two by separating into sort of a diagonal antisymmetric and a diagonally symmetric unit operator. This one will just sort of sit off to the side and take care of an overall phase. And the 3 remaining parameters, the coefficients of A, B, and C spinors, which Pauli calls Z, X, and Y. We've done a cyclic permutation of their order as far as Pauli goes, and Hamilton too. This one is the asymmetric diagonals is bilaterally balanced, and the C, this thing stands for all of these things that begin with C that correspond to getting something moving. These two together do not have currents. Current is one of the words that begins with C. So this is where we put all 3 of these together in sort of a democracy. Okay, now the standing waves, which are just due to the red and the yellow or orange A and B, are indicated by pictures of Newton-Hooke potentials for a real two-dimensional motion. And it's just a matter of rotating those. So that's all you ever wanted to do. You don't need the rest of the U2 group. But the rest of the U2 group consists of all of these phenomena associated with C. The one that normally is called Y. Okay, so X and Z are the real matrices. This is the one that puts in the, shall we say, the moxie or mojo or something to the quantum mechanics. And Pauli spin operators, X, Y, and Z, that's B, C, and A, were developed in 1927, mostly by Pauli and Jordan, but Pauli is his unique author of that paper. And they go with the Hamilton quaternions. If you just simply put an I on each of these things, you recover the original I, J, and K of Hamilton. Abstract operators that he wrote, and I just now realized I forgot to get a photo of his inscription into the pillar on a bridge in 1843. He was so excited to discover these operators in his head that he immediately stopped and with his knife probably spent hours carving the relationships, which we will be studying, of these operators. The group of multiplication table. This after you put all the minuses on makes a group of order 8. We're just going to break it down as an algebra of order 4. And that's what we're going to do with this. So, or I should say these. We're not so much interested in operators today that square up to -1. That's what Hamilton's quaternions were. He was trying to do further the Euler description that was so powerful in 2 spatial dimensions, x and y. He wanted to get that 3rd dimension, and he didn't realize that you have to do 4 in order to get the 3. And that's we'll be quite clear in just a few minutes here what I'm talking about there. So this is stuff that we've already looked at a little bit, and it's these how a matrices is squared a +1 that we'll actually use. But in the background, these will be there, and we're going to end up putting an I on them anyway. So Hamilton wins in the end of this story. Okay, so let's get started here. And now it's really a little bit annoying because I'm going to have a lot of notation, notation that's different from, slightly different from what you would normally see in descriptions, but very useful for some little job. And then there's another notation for some other little job. So we've got to sort of, this is a point where there's a lot of unpleasantness that I can't help with, at least not yet. I'm going to try as hard as I can. It would be nice if we could do all of our physics just with this relation, but that's not the case. This is only 2 dimensions here. We need 4, and particularly we need the 3 A, B, C operators. I should say the 4 because it's A, B, C, D, but, well, we'll make sense of this in a bit. The basic idea, of course, is that in order to solve that first order differential equation of Schrödinger, time evolution, we need to exponentiate the Hamiltonian. So we need to find ways to easily take the exponential of this matrix. We've already seen that we can use a spectral decomposition of this. If I had a spectral decomposition of this, no problem. I'd have to have 4 eigenvalues, and I would sum them up, and I would get all the stuff we're going to get. But that's a pain. We want to do better than that. We want to have a way to visualize. That's the important thing here. Most important thing, I would say, is to visualize this thing that's happening in 4 dimensions of space and time, really. And we're going to do the space part today in just a few minutes, really. Okay? So the key pieces of this mathematical bookkeeping, the way you state the sum of those operators, including the unit, okay, it's really 4 dimensions, but we're going to, this one I can just take as an overall phase factor and really kind of forget about it, because we don't know these states within an overall phase in any case most of the time. That's just a thing about waves that makes it an annoyance. But here is the notation that we're going to be playing with. We're going to be playing with this sum that's sitting in the exponential place here. This is the Hamiltonian. This thing is kind of just, as I said, going to be pushed to the side. So this, we're going to be mostly concentrated on the exponential of the first 3 things in a dot product of a vector made of spinor operators with a vector made of these numbers. And the first one is a minus d over 2. The second one is b. And the third one is c. Those coefficients that expand the Hamiltonian in terms of these very famous operators. Okay? So we're just going to split off the 4th dimension for a while here, and just let that be the phase, and then we're going to have this dot product times time, and this thing is an angular velocity. That's an angular omega for that goes back to the mathematician Darboux. And we'll talk more about Mr. Darboux later on. But right now we're just interested in this dot product that is this thing here. So that is a very important piece of the bookkeeping. Okay? And this omega dot times time, this thing right here, and you see I've written the omega as three components, omega A, omega B, omega C, and those are the values in terms of the A, B, C, D. Okay, but the time is being multiplied here. So angular velocity times time is angle. So we need an angle. And the angle letter that we're going to use is phi. There's going to be a vector phi, a little arrow on top of the thing indicating it's a vector. And that's the thing about this thing, is that there's this notation. Here I'm dotting a sigma operator with three numbers that are the components of this vector phi that we'll be dealing with. So this is kind of a nasty notation, and we try to shorten it. Mathematicians try to get rid of indices and all sorts of things, A, B, C, D. They sort of put that aside. But physicists, it has to become intimate with each one of these things, especially this guy with all his ability to make current. Okay, so we need to sort of straddle these two worlds of elegant notation. This is as elegant as I'm going to get here. Sigma phi, that's an indication here of a dot product. This is a very sophisticated way to draw it. Now, in the lecture tomorrow, Thursday, that's lecture 8 here, we will be talking about, if I can get this thing to move forward here, just to give you a picture of the operator space. The space where there is a vector in there that is sigma dot this phi vector that I've just shown you, that is A, B, C, D components, or X, Y, Z if you want to go and use the old notation. Okay, but I'm using the new one. B axis here, that's X. Z axis there, that's A. And C axis there, that's Y. Okay? This what I call the not so crazy thing that doesn't have any eyes in front of it. This one does, so it's really quaternions we're talking about over here. But in any case, these dot products that I've just mentioned are all being shown just as points on a sphere. You see, that would be a way that a mathematician would be pretty happy with it. It looks clean, you see. Very quickly gets dirty because we're going to put some physics into it. But in any case, that's this notation here. We're going to use it occasionally and try to explain as we go along. You can see that this is being made maybe a little complicated, but we're trying to do a lot of different jobs. Okay, so let's go ahead here and begin. I'm going to just keep this thing here for a long time while we do all the work that's needed to make sense out of it. The symmetry relations that we're going to be talking about for these spinors or quaternions is powerful, and it's made powerful by what they do with each other. We need to make a multiplication table for them. And right now I'm telling you what sigma x and sigma y and sigma z do when they're squared. And that is give you 1. I mean a unit operator. So that is the main heart of the U2 generator set, the one that really makes it do something. And U2 products are going to have to fill that table there. Okay? So for example, if I take sigma x, this guy here, we call him B for bilaterally symmetric, that's him right there, and multiply him by Mr. C, the great complex crazy, almost, it's another thing that begins with C, but I didn't use it because he's anything but crazy, so that makes things work. I multiply those two together, I get this. It doesn't look like anything I've had before, except if I take the I outside, factored out, I've got Mr. Z, or Mr. A, as we call him, asymmetric diagonal. antisymmetric diagonal is what he should really be called. Okay? So that's our first entry in the multiplication table. X times y is equal to I times z. Okay? Clear enough? All right? But when you do it backwards, that is y times x, you don't get the same thing, you see. This time I get I times minus. Okay? When I go backwards, I get minus. So there's an antisymmetric product, you see, that we're dealing with here. Now I should caution you, in a quantum mechanics course of normal things, they're not going to bother with this. Most of the people in this building don't understand why you would ever think of something like that. They've all been taught to do the commutator, which is the difference between this and this. Okay? And that'll be the same table, except there'll be a 2 here. But that's being messy. Okay? We're going to make use of what are really called algebras or rings. To do a commutator thing is called a Lie algebra. And we're going to stay away from them for a while for reasons that you'll see. This is actually a shortcut to a lot of the stuff that we need to do. Now if you go x times z, okay, now x of course is the bilaterally symmetric b, and z is the a, okay, so this is b times a, okay, we're using our notation, and it gives c, which is y, okay, but with a minus I in this case, okay, so I get a minus here, where I got a plus here, I get a minus here for this product. But surprise, surprise, when I do it reverse, I get a plus I down there. Okay? So we're almost done with all that you need to know about the U2 algebra. The thing that would lead to the group of quaternions. And there's the rest of it right there. Y times z is plus I times x. Y times z plus I times sigma x. Okay? So this is just taking the matrices that we've been given here and making an algebra out of them. So far, so good? Okay, makes sense? Okay? All right, we're going to do some stuff with that. And I want to point out that these things are really not so special. Each of them squares to 1, okay? But so does any other component of this vector sigma. And that's why this is being called a vector. I can make a sigma A based on any unit vector. Okay? A unit vector being a vector, it's got a little caret on top of it. That's sort of a Gibbs notation. We're going to see, I think you see already where Gibbs gets his ij's and k's. He went over to Europe and learned this crap. And he came back, I can't teach this to Americans, they'll go crazy and shoot me. So he just turned these things into ij and k unit vectors. And that's your calculus books now, right? Still, to this day, right? He emasculated Hamilton's work in order to satisfy the silly Americans. Okay? But, well, that's fine. We still like to use his dots and crosses, so let's not make too much fun of Mr. Josiah Willard. In any case, we have here that I will just simply require that the sum of those three numbers add up to, their squares add up to 1. Then a sigma that's made out of that is going to turn out to satisfy the same results. That's really cool. This is what really was probably part of the aha that Hamilton realized. Simple arithmetic, that I could write this thing like a vector. Okay, I'm here defining the spinor vector operator. Okay, this sigma, this would be sigma phi here multiplied by some number. Okay, but we're meaning a dot product with that vector there. Okay, so we're having little complex numbers sitting here, here, and here, and then those three operators, x, y, z, our friends x, y, and z up there. Okay, that's defining any linear combination of these three things is also going to be obeying the same multiplication relations if you do it right. What's doing it right? Well, here I go. I'm going to say that sigma a squared is just the product of those two. This means the operator sigma a times itself. And this operator is a linear combination given by coefficients of the unit vector, little lowercase a. Okay? So here's this thing, and here it is again. And that means 9 terms. Okay? And we need to sort those coefficients off to the right. Okay? Push the whole thing here. So I have the complex numbers, 9 of them here. Even carefully colored, except I missed the color on those somehow. But nevertheless, I've got XX, XY, XZ, YX, YY, YZ, and then ZX, ZY, and ZZ. Okay? I got 9 things here. Doesn't look like this thing is going to turn out to be 1. Okay? But let's just see. Okay? Because of the anti-symmetry, that you might call it anti-commutation of these things, this guy's going to cancel that guy, this guy's going to cancel that guy, and this guy here is going to cancel that guy. You can color the x's so that you see who matches. All right? So they're all gone, and I'm left with ax squared times 1 plus ay squared times 1 plus az squared times 1. And that then proves that this thing squared obeys the same diagonal multiplication as each of the 3, x, y, and z, or a, b, and c. Okay, does that make sense? So this is part of the aha. He's realizing now, you see, that these 3 things, any linear combination of them works. We're not done yet. You need to do this multiplication. Okay? What we're going to do here is we're going to do a dot, and we're going to get a cross product in the bargain. Okay? The way you do that is you take 2 different ones of these, sigma a and sigma sub b. Okay? Sigma sub a times sigma sub b. I just mean the sigma vector sum over coefficients associated with a vector a times a different vector b. So these are 3-dimensional vectors in 3 space, and as long as they're not lined up, I won't be repeating what we've just done. I'll be getting a whole new ball game here. This is with all A's, this is with all B's. Okay? So, again, we get 9 terms, but now there's not just squares of A in there, there's A's and B's. Okay? Separate the coefficients out, put in the minus signs where you see, well, it's the same. So ZX is minus XZ. XZ has been turned around here and put a minus sign on it, makes it right, according to that table. Okay? And I do the same thing with XY and XY down here. Okay? Of course, complex numbers commute, so I didn't have to worry about that, but I do have to put a sign on because of the operators. All right? So there's your product, and this must have been part of his great aha moment. Had to be, or he wouldn't have been excited about it at all. Okay? So basically what's happening here is I'm replacing each xy by what its product tells us. I sigma z in both places. Okay? And then I sigma y in both places on the corners of this array. And finally these two. Our first operator for Pauli, our middle operator B for us. Okay? So you notice y taking off the extreme side. That's our C. And then there's good old A right there. Okay? All right, let's sum this up. First of all, our diagonal, okay, that sum right there adds up to 1, or adds up and then multiplies the unit operator. Then I pull off our x, which is the first for Pauli, okay, and I get a antisymmetric combination of the y and the z. Okay? And then I pull off the x and the z combinations. Okay? So I get an I times that combination of a, z, b, x, and a, x, b, z. All right? Those wouldn't have been there if a and b were equal. Right? And finally, the last one, which is our first one, is the sigma z, or our sigma a, and it's involving xy, ax by minus ay bx. Okay? Well, that's pretty cool, because that gives you this relation. Multiply these two together, and you get a unit operator with a dot of the two vectors, and then you get a dot with a sigma operator, and you use the cross product. That's what this vector here, this is a complete cross product in 3 dimensions. Cool? Very cool. You can see why he stopped and carved this thing in. You know, most people are excited with some girlfriend and they carve their initials into a tree or some piece of wood, right? That's very common in this country, right? And they deface the national parks in many different ways by doing this, okay? Now here he's defacing a bridge in Dublin with one of the most amazing pieces of algebra that the Clifford algebras were discovered at this point. They're the ones that are in the Dirac equation. Now I should point out that he knew about this. He had to. I don't see it in any literature, but when we do our calcium mechanics, our complex variable review, I point out that A star B, that's AX plus IY star, means conjugated, okay? That means AX minus IAY times B, complex number, BX plus IBY, okay? I multiply those two things together, and what do I get? Well, the real part is AX BX plus AY BY, which is the dot product in 2 dimensions of A dot B. But I also get the only component in a 2-dimensional setting that is the Z, big Z component of A cross B. Okay? So this is where I make a point that if you want to understand complex variables, you can also understand 2-dimensional field theory and all the divergences and curls and integrals and all this crazy stuff that happens in complex variables by simply following this up. And I recommend that you read that in the Classical Mechanics for with a bang. This is a very, which almost boils down to a complete course in complex variables that you can take in an hour. Okay? So he knew, he must have known about this because this is the generalization of it. You see. And that's what we're going to use over and over again. This thing plays such a role in group theory and dynamics of 2-level systems that we, you know, it's something, if you, everybody tattoos things these days, so if you're going to tattoo a formula, that'd be one. Okay, that's really, really cool. All right? Now, the exponential. This is where it gets weird. How do you take an exponential of this thing and get it so you can just write it down? All right? So the idea here is that Hamilton is now, and this is something I'm sure that came later, but he must have realized he could do this now, once he got that algebra going with his little dot and cross. He realized that he could take exponentials that, like the Euler, to generalize the Euler theorem, Euler de Moivre. So the power series here, you see, is broken into 2 parts. The even powers and the odd powers. Okay? And the even powers make a cosine, and the odd powers make a sine. The odd powers, you see, even powers are plus or minus 1. The odd powers are plus or minus I. So it nicely separates into real and imaginary parts of this exponential. Okay, so that's the proof of the Euler theorem. We need to simply extend it, you see, with this cyclic behavior. I, well, let's say minus I, because that's the one we like to use. All our phasors go clockwise, which is left-handed, so we put a minus on there. This minus I to the 0th power, of course, that's plus 1. By definition, you might say minus 1 to the first power. Well, by definition, it's minus I to the first power, excuse me. Minus I squared, well, we know what that is. It's minus 1. So there's your plus 1 and minus 1. Now you have minus I, and this thing with an extra I on it, you see, gives you plus I there. And then finally plus 1. You have to go to the 4th power in order to get this thing to 1. Then it all starts over again. Okay? So this cyclic behavior sets you up to use this to take care of this. Take care of this 4-dimensional Euler theorem. Okay? Now, at this point, we're going to take this notation here, particularly that one right there, and divide by the magnitude of this vector. Okay? Magnitude of this vector is the sum of the squares under a radical. There's the magnitude, which is being put in the denominator of this to make what we call a unit spinor vector operator, or unit operator vector. You sound crazy when you put all of the stuff that you know together to make comments about what we're doing here. You almost need another language. And so this combination of A, B, and C that we were talking about, that's in an exponent here, divided by the sum of the squares of those numbers is, and by the way, until we do relativity, we don't need to consider complex values for the A, B, and C components. The time part requires imaginary. It's crazy. That's even crazier thing, but it is absolutely the case. Okay? So here is what you're getting as you go through the powers of this sigma, any component, you see, a sigma of any component. I don't care what vector you're picking. It can be the phi vector with any real numbers there. That if you normalize it by taking out its magnitude, you're in business to do this exponentiation that we're talking about here very easily. So this allows Hamilton to generalize this e to the minus I phi, the nice harmless e to the minus I omega t. That's what phi is. That's the angle you actually turn on a phasor of some kind. And this is the frequency, which would be energy in quantum mechanics, that drives that rotation of the phasor. That we're going to be able to generalize this to e to the minus I vector phi with a vector operator, the operator that has a component in the phi direction, just like this diagram that I was showing before over there. So there is our combination right there, with no restrictions on the components to be normalized, but later on we're going to be working with this thing here all by itself, you see, this operator that has a phi component, but the component is in a direction that's specified, but the normalization of it is 1. You see, so that's the thing that makes the notation crazy. But once you get the idea of what we're trying to do here through, you can then just go ahead and write this down. Now I find a humorous way to describe this. But anyway, this is the old Euler thing. This is the new 4-dimensional thing. This is only 2 spatial dimensions. Or 1 space and 1 time. That's kind of weird. But in any case, that's what we've got. A 2-dimensional thing here, and then we've got a full 4-dimensional, really. But we're only interested now in 3 dimensions. If we constrict ourselves to real values for these, if we stick to that, we're doing what's normal quantum mechanics. Okay? I make fun of this. I say, this is the crazy thing theorem. If you have a crazy thing whose square is minus unit of some kind, then e to the crazy thing times some number, parameter, okay, angle, okay, is equal to the cosine of that angle times the unit, whatever the unit was, plus the crazy thing times the sine of that angle, whatever phi is. Okay? So, here are two examples of the crazy thing theorem. First, suppose the crazy thing is minus I, or plus I, or any other phase. Okay? This crazy thing is just square root of minus 1. That's crazy thing, right? Crazy thing is minus 1, right? Square root of minus 1. It's actually minus the square root of minus 1. Okay? Here, I'm taking minus I times sigma phi. That's what we're actually doing right here. These sigma phi operators being exponentiated. Okay? It's got to have unit vectors. I've taken its actual value off of it. I mean, this sigma dot, a unit one of these vectors. There's the caret to indicate that. That's the same as sigma dot, the actual thing, phi with a vector over it, divided by the number phi, the parameter phi, the angle, phasor angle. Okay? Here we have this crazy thing. And what we're saying is, we're saying that e to the I that, there's the parameter phi, is simply equal to the unit times the cosine of that angle, okay, minus I, and then the crazy thing. The whole crazy thing is right here, minus I phi. We're adding that crazy thing up here, complete with its minus sign. And then we're taking the function sign of the parameter, just like the cosine of that parameter is there. And that's it. This is the meat, the mathematical meat of this whole development. And this is something that Lie worked with. Lie came much later, you see. He's trying to generalize that for huge matrices, not just two. Okay? We'll see how that comes out later on. Okay? But this is a beginning. Really important beginning. Because almost all the stuff we're doing with quantum electronics and quantum photonics involves at the very least two levels. First, two levels of polarization, and secondly, two levels of some state that polarization is exciting. So, you know, it's a very small and insignificant looking thing here, and it's crazy. It seems that way. But it's crazy like Fox. A lot of animals act crazy, so their predators will be misled. You know that, right? The fox will act very crazy to get the predator over here, and then the little cubs are safe. A lot of birds do the same thing. Right? Okay. So, now we got to get to some more about the geometry. We need to connect with the three vector that consists of A, B, C, and the U2, which consists of, say, spin up and spin down, or polarization X and polarization Y. Okay? How do they talk to each other? As I said, one of them is twice as big as the other. We get that idea down later. So here we are back to our simulations, except now I'm just rewriting what this generalizes. I've taken off the crazy thing, but I've left it down here. This is the crazy thing that we're working with all the time. There's the original one with any value for the parameter. It's the crazy thing times the parameter. Okay. Here's the parameters phi. Over in 3 space, we're going to probably want to use thetas more often than not. We're going to get into that. That's the factor of 2 business that plagues this mathematics. At least it does, because humans have to use this and they get sick very often using it. But here's where I'm going to go ahead and use the crazy thing theorem. I'm going to say, okay, I can find the exponential of the A matrix. Well, actually, that's pretty easy because it's diagonal. We really don't have to do much work. But let's just follow the rules, okay? Our crazy thing now that we're multiplying a real parameter phi A by is minus I times sigma A. Okay? So what I got to do is take the cosine of the parameter times the unit matrix And then I got to take the crazy thing, which is minus I times 1 minus 1 matrix. That's the A matrix with a minus I attached to it, and multiply it by the sign. So that's what we're doing. Okay? That's right. And now this is pretty obvious. You should have been able to get this one without all of this rigmarole. Because when I put these together, I cosine minus I sine, get nothing for the off diagonal, and then I get down here the same thing. Let's see if that's right. Cosine. And that's a typo right there. That should be plus. Okay? There should be a plus sign. This is correct. So it sure shows that I did this thing backwards, or else I made a cut paste mistake there. Okay? So this is the answer, obviously. It's this matrix with those coefficients in there, minus I and plus I, you see. Okay, well that's the easy one. Here's example 2 with this is our big boy, this is or girl. This is the curly Coriolis current carrying operator. Okay, what does it do? Okay, so here it is. Here's our crazy thing. Minus I times the C matrix right there. Minus I times 0 minus 1 I plus I. Now it takes a little bit of focus to see the I's in there, but there's what we're dealing with right there. Times minus I, okay? So we're putting that whole thing as a crazy thing right in front of the sine wave, and we're putting the unit in front of the cosine wave. And we're adding it up, and we're getting, ooh, look at that. That's a rotation matrix. Wow. Okay? That's what makes C curly, or Coriolis. Okay? That's what makes the Y a rotator. Now notice we're doing an entirely imaginary thing in the exponent with an I. That makes it entirely real, so this thing has to come out real. This is a real matrix, this one is not. Now these are the two operators, the Z and the Y, that we will use forever to do manipulations computationally. And the reason for that one is, this one is cool because it's diagonal, but it's complex on the diagonal in general. This one is off diagonal, but everything is real. So you don't have to do complex arithmetic when you're doing this one. Whereas you involve this one in there and you do have to, but you don't have as much of it. So that's why they pick these two axes, Y and Z, or in our language, A and C, to do all of the operations when we combine these things. And we have to combine them in order to solve the differential equations in general. Okay, now here's the general result. I don't need to belabor this, but this is a complete solution to the exponentiation here for all possible values of your phase angle or your angular frequency. It's completely general. Okay, this is the real McCoy. This is what we're after here. This is what Hamilton probably was after. The ability to build this matrix here. For any vector direction, and that would be a unit vector direction, right, that he's using here. These are the coefficients divided by the square root of the sum of their squares. Okay? So that's an important caveat, as our crazy thing here is a unit operator. It has to be sigma sub phi is sitting right there. That phi component of the operator sigma. And that's the dot product divided by the parameter phi. And that's why we're putting a unit caret on top of the phi there in our crazy thing. This is a general crazy thing. Okay, so this is a little bit more complexity. The notation is starting to show itself here. Is this making sense? Is there anything I can say? Well, there isn't anything I can say that is so good that you don't have to study this. You'll have to go back over to this. Obviously, I didn't get it the first time either, even though I had Feynman to help me with things like this. And of course, he was pretty much absolutely no help. He figured you should learn it yourself. The hell with you if you can. That's sometimes the way it is.
Bill?
Yes?
Before you go on, that first A-type evolution operator in
This guy and this guy?
Yeah, one more line down where you've got it written in terms of the exponents of the
This one right here.
the B angle. So that phase shifts one way and it phase shifts the other state the other way,
The other
equal
way.
amount.
Absolutely. That's right. And we're going to see that coming out effectively in all of the examples we do. We'll see that there's always this balance. The determinant of this thing is 1, but that's also true for this one. They're unimodular. Okay. All right, so once again, here's the A and there's the Y. There's A and C, or Z and Y are all sitting there. And what we would like to do, we'd like to test these operators by making them rotate each other. Now, that's a good thing that you've got to get familiar with, is you've got to think about these operators in terms of having a vector that's associated with them. Now, the vector that's associated with them is abstractly stated on the first slide of the next lecture over there to the right. But let's swing the camera over to that. In the meantime, show this device here. This device, which has vector components phi sub A, phi sub B, and phi sub C, or X, Y, and Z, is the crank that will drive all of the other things that might be on this table here, so to speak. That includes an actual spin vector, which would be inside this sphere, but also the whole sphere, you see. It consists of a coordinate system that's out here able to turn. So this is a much more, I should say, fruitful way to think about than the abstract mathematical one that just says, hey, there's a vector connected to any possible spin or operator. It has 3 components, X, Y, and Z. We're calling them phi sub X, Y, and Z here, or A, B, and C. So when it comes time to rotate things, we could have an operator here which we would rotate like any other vector, but that's getting a little ahead of our story here. Let's see what it is we're really trying to do. This 3D axis vector, I call it a crank. It literally is a crank. There's the handle. We're going to turn that crank for a number of problems that we'll do here. But that axis vector is the generator, you see, of a rotation. You exponentiate it, get the whole rotation, and there's the crazy thing theorem giving you exactly the rotation that you're going to do in the shorthand notation involving the 2 terms of cosine and phi. So we're going to have some axis that's any old place applied to various vectors. Say the unit vectors, the operators that we started with, as sigma A is in this direction, sigma Y is in that direction, and sigma X or B is in that direction. So there's a 3-dimensional Cartesian coordinate system, and we're going to come in there with some vector and rotate them. But let's start with the vectors we already have, like B or Z, or most likely we'd like to try this one out. But let's do this one first. Let's do the A axis, where I'd have a crank in this direction, and I'd take these guys and see where they go when I crank them. Okay? So the idea is that any 2x2 sigma matrix, that means any operator that's pointing in some direction phi, will be acting on the bras and kets that make up these sigmas, and that means that you have to do it fore and aft. You have to apply the rotation to an operator on both sides to take care of the kets, on this side, that one does that. Then the bras have to be operated on by the inverse, that is the R dagger if we're talking unitary here. Okay? So this is what we're going to do. We're going to take this matrix here and sandwich it and its conjugate as a bread around some other operator like B or C. We don't need to see what's going to happen. Nothing's going to happen to this if you rotate it because it's just a line. But these guys are going to have to swing. So that's what we're going to do here. We're going to take a rotation C, this guy here, and operate on sigma A. Sigma A consists of that matrix, the very first one we talked about, the asymmetric diagonal one. And then here's our inverse. It's our cosine sine matrix, but with minus moved down to here, and from there, and we'll work that out. Okay? So I multiply these two and get that thing. And then I got to multiply it with that thing. All right? That's what you get. Okay? This thing breaks up very nicely. And you see cosine squared minus sine squared, that's cosine of 2 phi. Multiply, and then there's sine squared minus cosine, that's minus times cosine of 2 phi. And then I get the balanced B operator, X-type operator for Pauli, coming here with a sine coefficient, you see. This is obviously sine of 2 phi, so it's this. Okay? So there's what you're seeing. You're seeing that the B operator acted on by C, the crank is in this direction. It's going to take the A and rotate it down like that, right-handed roll, you see. It's going to take it down and get you a linear combination of cosine of sigma A that will shrink down, and the sine will start with 0 and shrink up to give that A vector, which is in the plane of B and Z. I'm sorry, B and A, or X and Z. This is the kind of coordinate system you're used to, right? X here, Y here, and Z up for zenith. Okay? So these operators are behaving like vectors. Surprise, that's what we've made them do. When we write an operator using this vector by taking linear combinations of these three things, that's a vector operator. Okay? And there's the idea of the thing. The 3D rotation is twice. There's that factor of 2. This darn thing's going twice as fast as you might expect it to have done. Okay? Well, not okay. We've got to figure out what the heck's going on here, right? The 3D rotation is by 2 feet, twice the 2D angle in the spinner world, which has two dimensions, two complex dimensions, but still under dimensions. Okay. Try another direction. Okay. Using that vector right there. Okay. You know visually what's going to happen. You just picture these things rotating. That's why I built this machine, is to visualize arbitrary cranks. This is just a crank on the y-axis or the c-axis. We can have a crank anywhere. And that's the idea of this whole business, is you do that rotation. Here, for example, is that rotation of B, just to check. Okay, if I do the rotation again now, you see I'm doing this type of motion here. The B is going to be here, and it's going to get rotated down, remaining orthogonal to the A all the time as it rotates on that circle that is perpendicular to the crank in the C direction, in the Y direction. Okay? Again, the angle is twice. You can see it happening just as it happened over there. There are two operators, so you should expect to have to get something that's twice as big in terms of the result of the operation. Now, what about those mysterious factors? And now some more notation. We handle this in this particular class by using bigger letters for bigger rotations. We're getting a rotation in the real world, which is going to be down here, that's twice as fast as what goes on in the spinor world, the U2 world. Okay? So what I'm going to do is I'm going to say, I'm going to expand the Hamiltonian like I did before, and I'm going to have omegas. In this case, A plus D over T is just the thing that's the overall phase that we've kind of swept aside because it's unit operators, so we can factor out. And then I've got omega, little omega A, little omega B, and little omega C. And then I've got these sigmas, these reflection operators that square up to L1. Okay? That's the spinor world. Here's for the world we live and breathe in, a three-dimensional world. Okay? What have I done? Okay? What I'm going to do, you see, is switch the 1/2 that's here into the operator. I'm going to leave A minus D here and put the 2 in the denominator of coefficients of that. I'm going to do the same thing for B. You're going to have 2B here and 1/2 here. And then I have 2C here and this minus I over 2 instead of minus I there. The same for I over 2 on the lower part. Okay? But then this number and this number and this number is going to be given an omega notation, but we're going to call it big omega. Okay? It's twice as big. Okay? And then this thing here, this sigma, we're going to give it a big S, but S here means spin 1/2. This is where spin 1/2 makes its debut. For both, all three of the A, B's, and C's. Okay? So we're going to have two notations for the same Hamiltonian. One that is convenient to work in spinor world with little sigmas and little omegas, and another one that works in the 3D world with big omegas and big S for sigma. And big S means half as big as that one. So they're the same thing. They are equal. They are identical. All of these things here are identical to this. There's two different ways to look at it. 3D world, 2D world. Okay? So the idea is the components ABC switch a 1/2 factor from the omega velocity to the S momentum. Okay? All using the same well-known Pauli spinners, which go back to Hamilton. Okay? And here's the new stuff, the Jordan. J stands for Jordan very often labeled JX, JY, JZ. But S for spin or S for Stokes. That's what it really should stand for. Because he's 1843. These guys don't show up until the next century. They weren't even born when he did that. Okay? So, let's take the exponential of this thing. How do we write it? Okay? We've already been writing it using little omegas. Okay? We've got the overall phase with a little omega. That isn't going to change. We don't need to change that. We don't need to worry about that factor. It's not something we can easily measure until quantum information theory comes along. And that's why I'm keeping it, because you do need to know it there. But as far as the kind of experiments that spectroscopists have been doing to get information theory started, we would use a little omega and a little sigma, okay, or a little sub-omega and omega t, okay. There's the thing being written that way, and there's the crazy thing theorem being carried out, okay. Here's the way we do it in 3D vector space, okay. We'll have a big omega dot and big S, okay. Big omega is twice as big. The big S is half as big, okay. So in place of little omega A, little omega B, and little omega C times time, which is what we had right here, okay, I'm going to have big theta replacing little phi, big omega replacing little omega right there. That's going to be the definition of this thing, which is the angular velocity, okay, in 3 dimensions. And this one is 1/2 as big as that one. Okay? This is twice as big as that one. A minus d over 2, A minus d. B, now it's 2b. C, 2c. Okay? Make sense, sort of?
Yeah.
All right? I told you this was going to be a notational nightmare. You can see why people don't understand this stuff. It's pretty obvious. Okay? So, we're going to have a crank vector associated with each of these guys. A crank vector that turns a certain angle, an angle phi here, which is the square root of the sum of the squares of all the component angles. Or it's an angular velocity times time, which has got 3 components with little omegas, A, B, and C. A being Z, the B being the X, and the C being the Y, so I'm out of order here with respect to Pauli, but we're going to be doing polarization, so I'm in the correct order. And this is A minus D over blah, blah, blah. This is going to be twice that. This whole vector here is twice that vector here. There's the time, you see. So we're talking about here actual angles of a phase rotation. That's got the angular velocity times time in each spot. So this is a notation again for 3D vector space and 2D spinor space for crank vector. Okay? And this crank here, you see, is twice as fast as this one. Angular velocity is twice that. You see, multiplying the angular momentum to give you the action that is half as big. So that action comes out to be the same, and then better, or your phases aren't going to match. So here's the deal: a mysterious factor of 2 1/2 can be very quickly visualized with respect to spin up and spin down. I've already mentioned this. If we're going to be doing electron spin polarization, and we call this spin up and that spin down, those are the orthogonal states for that way of doing 2-level systems, which is Rabi, Ramsey, and Schwinger. Then when I start to do rotations, you see, in spinor world, the spin vector world is going to behave by rotating twice as fast. And you know this has to be because as I go from spin up, tick, 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 to spin down, I've only turned 90 degrees here. But in that operation, I have turned spin up all the way to spin down. So while I'm doing these little bitty beta over 2 rotations here, I'm doing a full beta rotation by a 3x3 matrix, actually, and this we're familiar with. Not by beta over 2, but by beta. And forgetting about the component that goes with the actual rotation operator, in this case, it's a simple example for that reason. So you see there's this 2-to-1 connection between the spin vector world, 3 real dimensions, and this crazy thing here where we have 2 complex dimensions, really 4-dimensional. This is a bigger world, and it goes half as fast. Have you seen this before? Mohammed, is this something that you've stripped over?
Just I'm thinking, are we studying one system in 2 different spaces?
Ways.
Yeah.
You bet. This is 2 different ways to look at any of those 2-level systems. Well, I just picked on spin up and spin down here to be ornery, because that's the one that you really have the most difficulty, and we're still wrestling with that one. But when this is X and Y polarization, you have a better feeling about that. There'll be a Stokes vector space doing the same thing, going twice as fast. And we'll show that very quickly here. We've got a few more minutes, I think. Before the battery, my battery and the camera's battery fails. So let's do that real quickly. Here's the weird thing, is that after I do a rotation to get the spin up, and then I do some more rotations to do a spin up, but with a minus phase factor, okay? There's spin up again, which is what we started with, but with a minus sign. You see, this one will just come right back and be home again. This will be the same as the one we started with. So it's telling you that something in our 3D world, like me, that does a rotation like this, I've got a minus sign on me now. I got to either go this way or continue, minus sign gone, I'm home. I literally have to rotate twice before I get home, if I'm an electron. And I don't look much like an electron, I don't think, but there are a lot of electrons in me, and they're subject to these rules as far as we can tell. So there's a halfway for the vector world. 2 pi is all you need to go here. This one's only halfway home. He needs a 4 pi rotation. I need to go clear out to here in order to get that one home. And that's true for any two-state system. And there's a lot of them, right? So that's the main point. Life in 2D spinor space is half fast. Poor joke. Theta equal 4 pi, 720, needed to return to the original state, the really original state, in a far better description, more complete quantum mechanical description of nature is this one. This one is just it's kind of a glimpse of what's going on. That's what we're used to. Our head is programmed for this one. It's not programmed for that. We have a hard time thinking about that one. Okay? Now let's stop for a moment and just do a real quick problem, which would be a Hamiltonian for NMR. Gyromagnetic coefficient, get the arrow out of there, times sigma operator dot B. That's magnetic moment is gyromagnetic ratio times a spin operator. This would be 2G, G equal 2 over 1/2 to really do it for an electron spin. So here would be the gyromagnetic ratio multiplying a magnetic field at Bx, By, Bz. Okay? That's the Robbie-Ramsey-Schwinger idea, is to take these guys and just sum them up and make one of these spinor vector operators. Okay? And it's got these funny names attached to it by us. Okay, but they were using a Z. I'm sorry, it looks like I made a mistake there. I should have had a Z right there, but we're using A, and then X and Y is what they use. We would have put a B here and a C there. Okay, so we have the order for us right, and then the actual naming for the old guys. Okay? So, what's happening? The crank literally drives the spin. If the spin starts to spin up, the magnetic field, B field, not to be confused with B unless the B field happens to be in that direction, but it's not. It's going to be in the omega direction. Okay? Omega dot T is angular velocity of these three components dot T. We're using our notation instead of X, Y, Z. Okay? So that's the thing for fermion spin. The omega is the GB field. The crank is that. So that's to make connection with the quantum mechanics that you'll probably be learning in the quantum course. Okay? That's where you see our stuff connected to the old stuff. Robbie Ramsey Schwinger stuff, 1954, okay? The question, though, still remains, how is the spin state or spin vector defined? What parameters, coordinates, does it have? And this is something that is, I think, really key to this. And this is what Lee would like to have done. He would like to discuss every other possible state as some rotation of an initial state, say Z up. Pick an origin somewhere in spinor space, get the state for that, and then build operators that multiply that. 2x2 operators or 3x3 operators. So it's at this point that I'm going to introduce Euler's definition of rotations, which is not something Robbie Ramsey and Schwinger, but later Norman Ramsey was very happy to see what we had done, and he bought a little slide rule that I made that's based on this machine here. In fact, he also wanted to make that machine for Harvard. And so I'm going to show you the Euler angle description of a state. Okay, and this is a picture of this machine without the crank. It's just a spin vector sitting there at some angle and some twist. The twist is the phase, as we're going to find out. The azimuthal angle is what we call the coherence of a spin state, and this is called the population inversion angle. But Euler angles come long before quantum mechanics. These are just polar angles. This is phi for azimuth, alpha for azimuth. This is the azimuthal coordinate. This is the beta coordinate, the tipping of the thing. So I have an azimuth here. There can be any angle in 360 degrees or plus and minus 180. Okay, and then I can go from spin up to spin down and back again, you see. So this thing doesn't look like a very good representation of the spin that we were seeing there, but it is, as it will turn out. Okay, so the Euler angles are just the dials on this thing. That's what makes it important to see, is they are coordinates. They're not angles that get tangled up in commutation problems with that you will see for some others that we'll define. But there's an old-fashioned astronomer's diagram of Euler angles. Alpha, beta, and gamma. And I thought it was such a terrible diagram that I spent all this time and money making a thing to really show that they're coordinates. The kind of coordinates that they use in telescope. The only thing that's new is there's a twist angle for polarization, so to speak, if you're talking about optical telescopes. Okay? Now here's the way you define a state of the ball. And this is how you use operators to achieve it. That's what we have to learn to do. We're going to follow Lee's advice. We're going to get all of the possible coordination of the system discovered by group operators. Once you do that, you see, you set all of the things it can do in a group. The group knows its multiplication rules, which will be infinite in number, but that's equivalent to knowing all the Feynman paths that this system could do. And that is the weakness of the Feynman paths, is most systems just seem to have an uncountable, infinite, number of ways that they can achieve any particular state. This limits that severely. So the deal here is that the first thing you do to set a given Euler angle with operators is start with this thing along the y-axis, and then you rotate using only two kinds of cranks. You use this crank right here, which is the Y crank. Remember, we said it's the one that's always going to have real matrices. And then you use this one, which is the Z crank, and remember, it was always diagonal, but usually complex. So that makes the arithmetic easier, you see. Well, it also makes the visualization easier. So we're going to start here with these things lined up. That means I'm going to have the minus x-axis pointing toward me, the plus x-axis of this ball pointing towards you, and the a-axis is indicated on the aluminum there. And I'm going to set, my first job, you see, is to set the gamma angle. So I set my crank down, engage the suction cups, okay, so got them engaged, and then turn to some value, okay? Remove the operator and go down and set the thing on the y axis, okay? And that's the operator that really gets this thing going, shall we say, from spin up. This thing is still spin up, it just has a different phase, okay? And then I turn that thing using right-hand rule to tip it somewhere, okay? So I'll point it up there almost 90 degrees with respect to what it was, okay? That's this operation right here, sets the beta dial, okay? And then the last one is another Z rotation, okay? And you can see obviously they don't, these two operators don't commute. Now I'm going to set the azimuth, okay? Any value I want, okay? And now here's the actual representations of those operators. And when you combine those, you get the famous Euler matrix for rotations, okay? Now, I think at this point, we're running out of time, but I do want to point out something. That the first column here is the polar coordinate representation of the z bar axis. It has an azimuth alpha with a cosine and sine. It has a polar beta. Beta rhymes with theta, our usual designation of that angle, with a cosine here and two sines. Then all the others are there too. All the others, the y bar and the x bar, are sitting there. And then, if you're the passenger of that thing, and that's the real important thing that I want to get through this course, is the duality. If you're the passenger, the actual spin, and you're watching the universe go around, there, you see, is where the zenith of the universe is. And it's also a polar thing. It's cosine sine, but a minus for each of those angles. Cosine doesn't change, sine does, so I get a minus sign here. Here they both change minus, gives me a plus sign. So it's the same form as this, it's just it's using this thing right here as its azimuth. They're tipped up, that's their azimuth, that's their beta. They share the beta with the universe. That's the connection between the quantum object and the classical thing that's measuring it, if you want to be prosaic about what we're really after here. Okay? So those are the body frame polar coordinates that you're seeing in action there. And it's that sort of thing that lab view frame versus bod view frame that we're really trying to get people to understand. Because it's so powerful to have that group. Every time you make a group, you've got two groups. You don't ever have a group. You've got two groups, each of them capable of doing rotation. So now we're going to talk about cranks, but we're probably at the end of our tether here. I would like to, however, point out how the spinners work. Look at this. I'm going to do a gamma around z, that sets the phase. Then I'm going to tip it with beta, okay? That sets the spin vector at some angle. And then I set that spin vector around in an azimuth using the third rotation, which is this one right here. And so what that does is give me a rotation matrix. That's a very famous representation of U2 that we will use over and over again. It's really what I call the Euler representation. And if it's operating on a spin up with some amplitude, okay, or phase, you see, here's a general way to make the most general U2 state. And there are the parameters right there. And there's the relative phase, alpha. There's the beta, which is the population angle, and it's over 2, you see, because everything's in spinor world is half as big as what's going on over in the vector world. and that is the way you get. Now, we go ahead and we make expectation values. This is stuff we'll do at the beginning of the next lecture. But just to give you a feeling for it, there's polar coordinates again for the expectation value of the spin operator. 1/2 sigma A, B, and C, that's Z, X, and Y, is giving me this polar coordinate. That was the Z, so I get a cosine, and then I get a cosine alpha sine beta, and a sine alpha sine beta, with the, what we call the intensity, actually, the square of the thing. That's because we are squaring here. That is the actual coordinates of the spin vector. You see, it's polar coordinates, just like we got here. Okay, so that's what we're really after there. Are those three values. Asymmetry, balance, and chirality are continuous variables that really need to be known better for this. This is a summary here. This is the U2 picture, this is the spin vector picture, this is the phasor picture. We're trying to get all of these pictures into one head, namely yours. Okay? Now, there's the Stokes business right there. Okay. This is the polarization space with ellipses oscillating, two phasors oscillating. Here are the actual polarizations as points on a sphere, and that's the Stokes vector representing that ellipse. That's the stuff we need to understand. There's a crank that's making them move. So this is stuff that we'll spend the next lecture on, probably, with some animations showing how it works. So this is a summary of the world as we see it, involving two states. And there's a 3D world that goes with it. So I think we've, in a sense, made it through this lecture, but we need to fill in the details of this in a way that you can understand it. So I would recommend, as a homework assignment, reading this lecture and maybe even the text that goes with it, and then you'll come better equipped to see what we do next. Okay. And we may